Yes.
Okay, so we have this open-ended manometer, right? And if you guys remember, we had talked about how we would go about doing the calculations. So what I'd like you guys to do is use that insight that you guys know to figure out how to answer these 3 questions, right? I'm going to put you guys into 3 groups to give me 3 answers. Group 1 is going to be responsible for giving me the answer to A. Group 2 is going to be responsible for giving me the answer to B. Group 3 is going to be responsible for giving me the answer to C. Okay, take a picture. I'm going to put you in rooms, and you have, we'll say, 5 minutes. Is that cool? Excellent. I'm glad to hear it. Love hearing you guys talk. You guys are just so chatty today.
You stressed me out, Dr. Henry.
That's my job. If I don't stress you out, that's life, baby. Sorry.
I was taking a picture. Sorry. Yes, I'm ready. Sounds great.
Yes. So life is about a little bit of stress. If I don't give you that stress, you're not going to be ready for real life. I'm just helping you guys get to that point. Okay? Breathe. Just breathe.
There.
Okay, good. Okay, your groups have been created and rooms are open. Not just the answer, Christian.
I'll write ours, guys.
I got ours, guys.
Dr. Henry, this is where we needed your help.
Where do you need my help at?
From here, because I know we have to get to KPA.
Okay.
And Kayla told me, I didn't look at it, so I don't remember it, but something about something is in meters squared or cubed or something.
Okay. So we're not talking about volume, right? So if we're not talking about volume, and we know that millimeters of mercury so 760 millimeters of mercury to be exact, it's going to be equal to an atmosphere. So why would I want to get to meters?
I don't know. I didn't look at it.
Okay. And then if I also know that 1 atmosphere is equal to 101.325 kilopascals.
Well, let me go back to this.
So would that be able to help you?
So I go from centimeters to millimeters?
Yep. So what is the difference between a centimeter and a millimeter? How many millimeters will equal 1 centimeter? So 1 centimeter
10?
equals how many millimeters? What was that?
10.
Okay.
You delete this though.
Does that make sense?
Yeah.
Kayla?
Yeah.
Okay. So break it down. You always want to try to find the simplest route when you're doing dimensional analysis. It's always the simplest route. And isn't this much more simpler than trying to go from meters to?
Yes.
And I would put 760 down here.
That's correct.
Where'd it go?
It's
Oh,
down
there.
there. Yep.
This? Or am I wrong?
You tell me. Come on, have faith in yourself. Does that look right?
Yeah.
Then it's right.
Okay. I need to find my calculator. Found it. Does 15.68 sound right?
Let's see. Plug it all in. Let's see. You said 15 point.
68. This is what I got when I plugged it in the calculator.
No, doesn't sound quite right.
Maybe I didn't do my parentheses.
Make sure I'm looking at the right problem. Okay. So where's A? I can't see A. Where's A? Christian, where did you do A?
It's in the top right corner.
So this one where there's no lines and anything to help me understand what you. Okay.
Like that.
Dr. Henry, I still got 15.68.
Okay. Okay. So let's start off with, there's a couple of things that we need to remember, right? So if you guys remember with an open-ended manifold, right? How does an open-ended manifold work? Do you guys remember how it worked?
No.
No?
The gas pushes on the stuff in the tube and pushes it up.
You're saying, the gas from outside?
No, this ball. It pushes
so the gas, it will push it up, right? But is this guy pushing it up, or is the pressure from the outside pushing it down?
The pressure from the outside.
Yeah, Marducio says the pressure from the outside is pushing it down. So we know that the pressure from the outside is always going to be what?
Larger.
What was that?
Larger.
We know it's going to be larger. Yeah, that's right. We know that this is going to be larger because the mercury is being pushed up in the other direction. We also know that the pressure from the outside is going to be what value?
14.7 psi.
14.7 psi or 1 atmosphere. Is that correct?
Yes.
Okay. So 1 atmosphere, we know that is atmospheric pressure. Okay, so if we know that it's atmospheric pressure, and we know that this guy is being pushed up by so many inches, right? So let's see, Christian had did it in terms of inches of mercury, right? So what is the 1 atmosphere is equal to how many inches of mercury? I wrote that down somewhere. Old age here.
760.
760, right? And remember, we're saying that Cassie just told us that the pressure from the outside is greater than the pressure of the gas on the inside, which means that it has to be less than 760 psi, right? Or 760, not psi, 760 millimeters of mercury. Now, Christian had actually did the calculation here where he changed that distance that it's changing, meaning that it's being pushed the other direction by 4.63 inches, which turns out to be 118 millimeters of mercury. So we should be subtracting to get the actual pressure of the gas, because we know that it's less than atmospheric pressure, by that difference. So my gas, in the case of Christian, is just going to be the difference between atmospheric pressure minus the pressure and the change. Now, what was that?
Go ahead.
So if it was the other way around, where the mercury bar was up here and the air was all the way down here, that would say that the pressure of the gas on the inside is greater than the pressure by this difference. So then in that case, we'd be adding. Do you guys see that?
Mm.
Okay, so now that's going to be really important. So when you're reading that manometer, depending on the direction that you're in, you're going to either be subtracting from atmospheric pressure or adding to atmospheric pressure. But atmospheric pressure is what we're going to be using as that baseline and making that adjustment in height. And that makes sense, right? Like logistically, can you see it? This guy is clearly greater than atmospheric pressure, so it's pushing it all the way to the other side. I'll show you an example here in a second, okay? Or in the case of the other situation, right? In this case, right? It's less than, the gas inside is less than atmospheric pressure, but then atmospheric pressure is pushing it up by that side. So if we subtract that difference, we will get how much that pressure is of that gas, okay? So what do you guys get if you do the subtraction there? This is what I get. Okay. And if you take this number here, that 643 millimeters of mercury, right? And we convert it to ATM. So the way we convert that to ATM,
Put it on the top corner, Dr. Henry.
oh, I see it right at that. So you get, I get 8 something, right? So if I take this number 643 divided by 760, I get 0.845. Check my math, I could be wrong.
You wanted us to use their conversion because we just went from PSI to atmospheres.
Yeah, but in your case, you guys went from PSI, right? That's pounds per square inch, right? So you guys went, and this is what you're doing, you're saying pounds per square inch. So if you look at those units, right? Inches is not pounds per square inch. Do you understand what I'm saying? Okay. So that's a different set of units entirely. Okay. So here, that distance, because you're talking about that distance. So in that case, if you're trying to go pounds per square inch, you'd actually have to sit there and determine the force. And because pounds represents force in this case, and inches squared over pounds per square inch, that's inches squared, all right? So in that case, what you would do, you would just only want to convert, you'd first want to do the same calculations this way and then determine that way. So your methodology would not be correct because you're making an insinuation that 4.63 inches were pounds per square inch, and that's not the same. Do you understand, Cassie? And Jessica?
Me.
Yeah.
Yeah. Well, everybody in your group, because it's not just you, it's a group effort, right? And then the last group, Maddie's group, you guys just started off with this, where technically you should have also done the difference first. If you had done the difference first, you would have been correct. Your methodology of making the conversion is correct, right? So then we could have just kind of used what they have here for ATMs. And then convert to Pascals. So do you mind if I erase your answers here? So are you with me, Maddie?
Yeah.
And Kayla? So the concept, the thing that you guys you were kind of led astray was that you were thinking about the closed-ended manometer and not the open-ended manometer. Closed-ended manometer, we would just worry about the height. But we're talking about the open-ended manometer where we're taking atmospheric pressure into consideration. Are you guys good? Do you guys all see that?
Yeah.
Yeah.
Okay.
Yeah.
Okay. So we want to make sure that we understand the difference between a closed-ended and an open-ended, because they're going to give you two different readings on how you do the calculations. Okay. Can I erase? Are we good?
Yeah.
Okay.
Yeah.
Okay. So, oops, wrong way. So similarly, this is the exact same type of problem, right? So the very first thing here, are we going to be adding atmospheric pressure or are we going to be subtracting atmospheric pressure?
Adding.
We're going to be adding in this circumstance, right? So then we want to change this guy to millimeters of mercury, right? So we have centimeters of mercury. And then, Maddie, what did you say? 1 centimeter equals how many millimeters?
10.
So then this guy is going to be equal to 137 millimeters. And Kayla, you said 1 atmosphere is equal to how many millimeters of mercury?
I forgot.
Christian.
Yeah.
1 atmosphere is equal to how many millimeters of mercury?
760.
760 millimeters of mercury. Okay, so now I have it in millimeters of mercury. Kaylin, 1 atmosphere is equal to how many millimeters of mercury?
760.
Okay, I'm gonna, see, you should throw something at me. I'm glad I am definitely behind the screen because I definitely deserve something because I keep saying Kaylin. Kayla, you said 760 millimeters of mercury, right?
Yes.
And so how can I convert that to atmospheres? This to atmospheres. if we're starting out with 897 millimeters of mercury, how can I convert that to atmosphere?
To atmosphere. 1 atmosphere equals 760
Okay.
millimeters
So
of
one
mercury.
atmosphere. Yeah. And 760 on the bottom, right?
Yeah.
Okay. Okay, so now I have it in atmospheres, right? That's a 1.18. So if I want to convert it to pascals, Gracia, what am I going to use to convert it to pascals?
What was the question again?
How am I going to change 1.18 atmospheres to pascals, kilopascals?
I'm not sure, to be honest.
Okay. Alberto.
Yes.
How am I going to convert 1.18 atmospheres to kilopascals?
There's a conversion unit, but I don't know what exactly it is.
Cassie, do you want to help him out?
You're going from what to what?
We're going from atmospheres to kilopascals.
For every 1 atmosphere, there's 101.3 kilopascals.
Okay.
Dude, okay.
Okay, simple.
Now that I get it, yes.
Yeah. Okay, so now remember this earlier today, we were talking about tapping out, right? Now, I'm just going to tell you guys right now, you have 2 weeks. I am not shortening anything. If we don't go over it, it's still going to be your responsibility to learn it. So you're definitely going to get ideal gases, right? And technically, we have 1 more chapter to go over. So don't tap out now, right? This is not the time to tap out. This is the time to start buckling down. Make yourself buckle down. You guys are adults. You are no longer kids. You're no longer in high school. Either you're going to succeed based upon your merits, not on my merits, based upon your merits alone. So don't tap out now. So if you're not paying attention to lecture, hey, tough shit. The test is going to be hard. And I will make it that much harder because I'm insulted. You know? You guys are clear?
Yeah.
Yes.
Don't make it harder, please.
Yes, sir.
Yep.
Okay. Okay, so, we're going to be using pressure. And whether you like it or not, you're going to be using pressure in everything that you guys do. All you guys are talking about, I want to be a doctor. I want to be this. I want to be that. Then prove it. Learn this shit, right? Take the time to learn it. This is an important part of it. Understanding gases plays a huge part in doing the science, right? If you're an engineer, you need to calculate how much pressure is going to be generated when you're mixing chemicals during that batch reaction. Or if you're going through a continuous reaction, right? You're going to have to know those things. If you're going to be a chemist, if you're working in a lab, you don't want to blow up half the room, right? So you need to be able to do these calculations to understand what are going to be the consequences. Pressure is going to be building up. You know you're going to be making pressure from this reaction. you need to make sure that you guys have a clear understanding on how the pressure is going to work. And what does it mean, really? What is 1 atmosphere, right? You guys did the Mentos experiment, right?
Mm-hmm.
What happened?
Yes.
What was happening in that case? Why did it shoot out?
Surface area change from the carbonation.
We had a surface area change, but why was it rushing out? Why didn't it? I mean, because technically it's all done in that one bottle.
From the surface area, you get an increased production of CO2, and CO2 has gas. So that's why it explodes out like that.
So the question is, are you getting an increase in CO2? But is it really an increase in CO2, or is
It's
CO2
the pressure.
Well, is CO2 being released? Because normally CO2 is absorbed in liquid, right? It was absorbed in that water or in that soda, right?
Yeah.
But by us making those adjustments, that surface, right, we release that gas, causing all of the pressure to rush out because it's no longer solubilized in with the water, right? And so causing pressure to occur. So what happened with the rockets, with the bottle rockets?
Same concept, right?
What was that?
Same concept?
Say
With
it again.
same concept, but
Same
you got
concept.
the dry ice and the
Yeah. So we went from a solid state to a gaseous state, causing pressure to build up. Now, does that make sense? Well, because the solid state, did it occupy as much room as that gas?
No.
No, it occupied more because the gas occupies more as it expands, right? Why is that? Why was it the gas occupying more? Why is there more pressure generated with gas than that solid? So when we went from a solid state to a gas state, what would happen if we filled it up with dry ice? Christian, what do you think would happen if we filled it up with dry ice?
Say that again.
What would happen if we filled it up with dry ice?
The bottom.
Yes, the bottle.
I mean, if we close the lid, eventually it would probably blow up because releasing CO2 would build up in pressure.
Okay, so my question is, and I asked all you guys this question, my question is to you guys, why? Why did that solid piece, because you guys put solid dry ice, wasn't it solid when you guys put it in there?
Yes.
Why does it make pressure? I don't get that. Why isn't it just occupying the same space as that solid? Explain that to me.
Because the solid, right? Because when it reacts with the oxygen, it releases CO2.
But isn't dry ice just CO2? And was it really reacting with oxygen? So what were we doing? What was the concept? Did we change? Was there a chemical reaction, or was there a change in state?
Change in state.
There was a change in state. We went from a solid to a gas. Now, that going from a solid to a gas, what is difference between those two molecules?
A gas wants to occupy all of the space, and if there's not enough space, then it's going to go beyond that space. And that's why there's so much pressure created, and then it exploded.
So the gas is wanting to try to occupy more space because it's no longer all bonded to one little area. It's everywhere. It's bouncing off everywhere, right? And you're generating that space, right? And that's what we need to understand. Gases are going to behave differently than that solid does. Doesn't that make sense? That's why stuff blows up in the kitchen, right? Because we build up a lot of pressure. How many of you guys heard of people making alcohol in their kitchen? Bootlegging.
Yes, and I've responded to a couple of them too. It's great.
Yeah.
Dummies.
And 9 times out of 10, the reason why their spills blow up, why their kitchen blows up, is because of what? What do you think? Take a guess.
Because of the pressure that they're building up.
Because of the pressure building up in the steel. 9 times out of 10, it's a result of the pressure building up the steel. And as a result of that pressure building up in the steel, it also caused an ignition of the ethanol gas that is being generated. okay? It catches on fire because it's too hot, and it also causes a blow up, right? So, and that's because they didn't understand the effects of what? Amanda.
The pressure of the gas?
The pressure of the gas, exactly. Okay, good job. Okay, so let's talk about how pressure, volume, and temperature all kind of play a part together. Okay, so we're gonna kind of skip over this diagram. It basically just shows you a nice balloon, and that the fact that we've been playing with pressure for years and years and years. We've been making alcohol, we've been blowing up balloons, you know, 1783, we were blowing up the first balloon. So we've come a long way, you know, and now we have a clear understanding. And so now it's time for you guys to pick up some of these things. Okay, so you guys are already aware that these elements here are examples where we have elements that are gases. So gases can be elements. Gases can also be compounds. So all gases are going to have 4 things that you're going to be kind of dependent on. That's going to be volume, the amount, temperature, and pressure. This is how they relate to each other. We have what we call the ideal gas law. P for pressure, T, capital T for temperature, N for number of moles, and V for volume. PV equals nRT. RT, R, is the ideal gas constant. So we know what a constant is. GD, what is a constant? Tia, what is a constant?
Something that does not change.
Something that doesn't change. So the ideal gas constant is going to be a value that doesn't change. Now, we can modify it based upon units, but it's going to be essentially the same. It's just that we change that unit. That's what really changes the unit, not the constant. You guys understand what I'm saying? So if we have all the right units, the gas constant is 0.0821, and that's atmospheres, liters over moles Kelvin. Now it has to be in these units for it to be that value. If it's a different set of units, then we have to do the conversion to convert to those units. You guys are clear on that?
Yeah.
Okay, good. So now if we look at this, if the temperature goes up, right, and if we keep the pressure the same and the number of moles the same, what's going to happen to the volume?
Volume goes up as well.
It's going to go up. Okay. If we keep the pressure and the volume the same, and we're looking at the number of moles and temperature, if the temperature goes up, what has to happen to the number of moles?
Goes up.
Does it go up? If these are going to be held constant. If the temperature goes up, this has to go what? So we're saying T goes up, P and V are now going to be constant. So if temperature goes up, what has to happen to the number of moles?
It would stay the same as your pressure and volume then.
Is it going to stay this? Now think about what you just told me, right? Now these guys are constant, right? They're like a value, let's say 5, right? So they're 5. Now T is going to go up, so T is normally at 25. And then N is going to be some value. We'll say P over R is going to be 5. PV over R. That's going to equal 5. Okay, so that's what we're saying. So now, if temperature goes up from, say, 25 to 100, what's going to happen to N? If this is 5, is that going to go up or go down?
Well, clearly now my option is to go down.
It's going to go down if you think about it, right? Because you have 5 over N. It's going to equal T, right? So if temperature is always increasing, right, then N has to be decreasing because that's the only way that 5 is going to get bigger, right? Because if you had 100 here for N, then that means your temperature is going to be decreasing. Do you understand what I'm saying? So these guys are inversely proportional, right? Number of moles and temperature are inversely proportional, right? As temperature goes up, number of moles has to go down.
On our periodic table in the gas section, it says number of moles of a gas is directly related to pressure, volume, and temperature of the gas. So
yeah,
is that...
but what they mean is not directly, right? So this is actually inversely related, right? So number of moles is related to this. So you're saying that, hold on. They're saying the number of moles is going to be equal that way as a unit, right? But these guys, if you look at moles and temperature, they're indirectly, right? They're inversely related to each other. As moles go up, temperature is going to go down. But as moles go up, your volume and pressure are going to go up. They're going to be directly. So one way to prove that to yourself, if you're doubting me, is to plug in numbers.
No, I'm not doubting. I'm just saying that's what I was saying. That's why I was getting confused.
Yeah. Okay. Okay, so let's move on, and we got to stop. Okay, so low pressure. So when the plate is turned off, there's no heat provided. The pressure of the gas is going to be low. Okay. Mm-hmm. Now, if we turn it up to medium, what's going to happen to the pressure?
It's going to go up.
It's going to go up, right? And then if I turn it up to high, what's going to happen to the pressure?
It's going to go up a lot.
It's going to go up a lot. So that means that pressure is directly proportional, right?
Yes.
So we can say P is equal to K being a constant, T. So they're directly proportional to each other, right? So as pressure goes up, temperature goes up. And we can set them equal to each other by using a constant, okay? So we're going to actually stop here.